we discussed about bandgap reference, and we said we need a PTAT voltage and CTAT voltage to generate the reference voltage. So let's begin with CTAT voltage. CTAT means complementary to absolute temperature. That means if the temperature increases, the voltage will decrease. So if we pass a current through a diode, calling its current as I0. If we pass a fixed current through a diode, the voltage across the diode, I am calling it as Vd, is found to be a CTAT. That means if we plot temperature with the Vd, y-axis is the voltage. So if we pass a constant voltage through a diode and if we vary the temperature, it is observed that the voltage across the diode is decreasing. So we can call it as a CTAT. So the condition here we are saying is I0 is equal to constant with respect to temperature and supply. So how we will make this I0, how we will make this constant I0 with respect to temperature and supply, that we will discuss later. So we know the current equation, current through the diode. Here it is I0. I0 is flowing through the diode. So the standard equation for the current is I0 equal to Is into e power Vd by Vt. So here Vt is the thermal voltage. It is not the threshold voltage of MOSFET, it is the thermal voltage and its value is 26 millivolt at 300 K. Is is the reverse bias saturation current or scale current, and Vd is the voltage across the diode. So this is the basic equation for the diode current, and from this we can derive the voltage. From this, what is Vd? Vd equal to, you can write I0 by Is equal to e power Vd by Vt. If you take the logarithm on both sides, then Vd equal to Vt into logarithm of I0 by Is. So this is the Vd that we are seeing across this diode. So we mark this also important. So this voltage is, the dependence of this voltage with respect to temperature is CTAT in nature. We will go deep inside that, but before moving to that, what is the slope? How quickly it is decreasing with respect to temperature. So the slope is found to be minus 1.6 millivolt per degree centigrade. So this is a standard value that you can see in every textbook. They will say the voltage across a diode, if a constant current is passed through a diode, then the voltage across the diode will decrease with respect to temperature at the rate of minus 1.6 millivolt per degree centigrade. So this is not a fixed value, and this slope is not a fixed straight line. Okay, this is not an ideal straight line. There are variations in that, and we will come to that point later. But as a qualitative analysis, we can say voltage across a diode will decrease with a slope of minus 1.6 millivolt per degree centigrade or per degree Kelvin. provided that constant current is flowing through the diode. And the equation for the diode voltage, we derived it as Vd equal to Vt ln I0 by Ss. So this is a first order analysis. So we will go deep into this equation and we see how it is decreasing, and those details we will see. I am marking it as equation number 1. We have diode voltage Vd equal to thermal voltage Vt into logarithm of I0 by Is, and we marked it as equation number 1. From this we said dou Vd by dou T, that is rate of change of Vd with respect to temperature, equal to minus 1.6 millivolt per degree centigrade. This is what we got from textbook. And this is more on device physics. This is not the job of an analog designer to see how it is coming and what are the parameters affecting that. It's really a device job. But we should understand this equation very clearly to design the bandgap reference. So if we check this equation, voltage across the diode Vt equal to Vt into ln I0 by Is. It has two terms. First one is Vt, the thermal voltage, and the second term is logarithm of ln I0 by Is. So we will examine these two terms separately. The two terms, one is Vt, other one is ln I0 by Is. We will analyze individually how Vt is changing with temperature and how ln I0 by Is changes with temperature, so that we can evaluate the product. That means how Vd, the voltage across the diode, changes with temperature. So the equation for Vt is the thermal voltage, Vt equal to Kt by Q. So by seeing this equation we can say clearly that Vt is not a CTAT, because Vt is directly proportional to temperature. Vt is directly proportional to temperature. So this is a PTAT. Okay, in this term, in the whole equation 1, if we take only this term, this is a PTAT. And if we analyze, you can see it's a CTAT. But this PTAT is very weak and this CTAT is very strong. So that if we take the whole equation for Vd, this CTAT term will dominate, and the curve of Vd is a CTAT in nature, and it is a effective nature is a CTAT, because this PTAT is very weak. We will derive that equation. So we said Vt equal to Kt by Q. So dou Vt by dou T, that is rate of change of Vt with respect to temperature, is K by Q, and this is a PTAT. So I am writing this as equation 2. And now we have another term, the second term, that is ln I0 by Is. So the I0, we have ln I0 by Is. So the I0 we said it is constant with respect to temperature. So dou I0 by dou T will be 0, because we assumed it is constant with respect to temperature. We will come back to this point later. There are some issues in this assumption. We will come back to this point. But for the time being, we assume that I0, that is current through the diode, that is this current through the diode, is constant with respect to temperature. This is what we assume now. Now the other term is Is. Is the scale current of the diode, and it is an intrinsic property of the diode. So we don't have much freedom to change. but that depends very much on the temperature and process. So let's analyze what are the properties of the IS that varies with temperature. So what are the terms that IS depends on? So we have, before moving to another page, I have equation 1 here and equation 2 here, and we will discuss about IS a little bit. So the scale current IS of a diode is directly proportional to mu, that is mobility, and K is the Boltzmann constant, T is the absolute temperature, and Ni square, where Ni is the intrinsic minority carrier concentration. So I'm not going deep into that because that's more device than analog. But we should understand this for proper circuit design. So again, this mu, we can say mu is proportional to mu 0 into T to the power M, where we can say M is approximately equal to minus 3 by 2. So the IS has 1, 2, 3 terms, and this mu itself is dependent on the temperature with the relation mu 0 into T to the power M, and K is a constant, and T we know it's a temperature, and next term is Ni square. So this Ni square is proportional to T to the power 3 exponential minus Eg by Kt. So these are the dependencies of IS for the temperature. So it has dependency on mobility and Ni square and this T. So we want to combine all these terms so that we can write IS is proportional to the constant like mu 0 and K, all I am bringing to a one single constant named B. So this B represents all the constants. We are just using a proportionality sign here. So we just want to see the dependency on the temperature. We are not interested in the constants. So all the constant like K and mu 0 I am including in the B. So IS is proportional to B into T to the power. We have 3 here, and okay, let's write exactly the same way here. So we included the K in the B, and the T I am writing as it is, and Ni square we have to include. So before including the Ni square, I am considering the mu term, that is we know mu is proportional to mu 0 into T to the power N. So mu 0 I included in the B, and again we have a T which is proportionality, the power is M, and M is 3 by 2. I am just keeping it as M. And we have another term that is Ni square, that is proportional to T to the power 3 and exponential minus Eg by Kt. So IS is proportional to B into T to the power this 3 plus 1 plus M. We can write it as 4 plus M exponential minus Eg by Kt. So this is the standard equation for IS, that we can write it as equation 3. So we got IS proportional to V into T to the power 4 plus M exponential of minus Eg by Kt. So we can remove this proportionality term now, because anyway we are using a constant. So I am writing IS is equal to V into T to the power 4 plus M exponential of minus Eg by Kt. So I am modifying this equation 3. So now we have to find dou is by dou t. That is how is is changing with temperature. So dou is by dou t is equal to, we have two terms here, not two, really speaking we have three terms here. The B is a constant, and this is one term containing temperature, this is another term containing temperature. So I am taking this B as a outside because it's a constant. So B into, that is first term into differential of second plus second term into differential of first. So first term t into 4 to the power t to the power 4 plus m, first term into differential of second. So differential of exponential minus Eg by kt is exponential minus Eg by kt into minus Eg by k into minus 1 by t square, because we are differentiating with respect to t, plus, now I am writing the second term as it is, and exponential of minus Eg by kt into differential of first. So 4 plus m into t to the power 3 plus m. We can simplify this equation, that equal to b into exponential of minus Eg by kt is common to both, so I am taking it outside, exponential of minus Eg by kt. Then here we have t to the power 4 plus m into Eg by kt square. So this term is complete, plus we took this term outside, so 4 plus m into t to the power 3 plus m. Now I want to take one more term outside. I want to take this term also outside. So b into exponential, so b into t to the power 4 plus m into exponential minus Eg by kt, and multiplied by, so I took this term outside because of a purpose. If we took this term outside, we will get this term. This is exactly equal to our is. So I took this term outside, then so here is Eg by kt square plus 4 plus m into t to the power minus 1. So we took t to the power 4 plus m from here, so it became minus 1. So now I can replace this term with is. So now I can write dou is by dou t equal to this b into t to the power 4 plus m exponential minus Eg by kt, I replaced just with is into Eg by kt square plus 4 plus m divided by t. Now I can write dou is by dou t is equal to is into 4 plus m divided by t plus Eg by kt square. So this I am calling it as equation number 4. So till now we found the expression for voltage across the diode, that we call it as Vd. Then we found Vd is equal to Vt into ln I0 by Is. Then we wanted to calculate dou Vd by dou t, and we found this Vd is dependent on Vt and Is. So we individually found dou Vt by dou t and dou Is by dou t. So now we can find this dou Vd by dou t. So we have Vd equal to Vt into ln I0 by Is, this from equation 1. Then dou Vd by dou t, that I can write it as, we have one term Vt here and another term ln I0 by Is. So we can write dou Vt by dou t into ln I0 by Is plus Vt into dou by dou t of ln I0 by Is. So we got dou Vd by dou t equal to dou Vt by dou t ln I0 by Is plus Vt into dou by dou t of ln I0 by Is. That equal to dou Vt by dou t into ln I0 by Is plus Vt into dou by dou t of ln I0 by Is. So here we know that I0 is independent of temperature. That was our assumption, and Is is the term which is dependent on temperature. So we can write it as 1 by I0 by Is into minus I0 by Is square into dou Is by dou t. So we can write dou Vt by dou t into ln I0 by Is minus this I0 we can cancel, 1 Is we can cancel. So minus Vt into 1 by Is into dou Is by dou t. This is dou Vd by dou t. So here this term we found, and this term also we derived. This we will derive in equation 4, and this we derived in equation 2, if I remember correctly. So that is dou Vt by dou t. We know Vt is Kt by Q. So dou Vt by dou t is K by Q into ln I0 by Is minus Vt into Vt by Is into dou Is by dou t we derived in equation 4, that is here dou Is by dou t we derived here. It is Is into 4 plus m divided by t plus Eg by Kt square. This Is is common, so we can cancel this Is. So dou Vd by dou t equal to Kt by Q we can write as Vt by t into ln I0 by Is minus Vt by t into 4 plus m minus Vt into Eg by KT square. So in this equation, this term is very familiar to us. That is Vt into ln I0 by Is. That is the expression for voltage across the diode. So I can replace that. So dou Vd by dou t equal to, this is nothing but Vd by t. Vd is the voltage across the diode minus Vt by t into 4 plus m minus this Vt I am writing as Kt by q into Eg by Kt square. So 1 Kt I can cancel here, this Kt and this Kt I can cancel, 1 T will remain there. Now I can write dou Vd by dou t equal to Vd by t minus Vt by t into 4 plus m minus Eg by q into t. Now I can take all the t outside, so I can write dou Vd by dou t equal to Vd minus 4 plus m into Vt minus Eg by q whole divided by t. So this is the final expression for the slope of our CTAT, that is rate of change of diode current, diode voltage with respect to temperature. So this expression tells us how the voltage across a diode changes with respect to temperature. Now you can substitute the values and check how much is this value is coming. Now you can write dou Vd by dou t equal to, Vd is the voltage across the diode. So we can calculate this approximately. We are assuming it as 0.7 minus 4 plus m. M is minus 3 by 2 into Vt is 26 millivolt minus Eg by q. Eg is near to 1.2 electron volt. So Eg by q we can write as 1.2 whole divided by temperature. So now we are calculating the slope. Now we are calculating dou Vd by dou t at 300 degree Kelvin. So now you write the value dou Vd by dou t, that is our CTAT. We have the CTAT, so temperature, voltage, our CTAT will decrease with respect to temperature. So this slope is the dou Vd by dou t which we are calculating now, that is 0.7 minus, this term will be a small value, that is 4 minus 1.5 into 26 millivolt, that is 65 millivolt minus 1.2 whole divided by 300. So the values we put are approximate values, so we will not get the exact dou Vd by dou t, but we need an approximate value. And by observing that, we can see that this term, the middle term, don't have much significance here. This term, the first term, the Vd, and the last term, that minus Eg by q, is actually playing a major role. This middle term has the very little effect on the entire equation. Why this is important? Yeah, this is really important, but not now. We will come back to this point later. This point is very important. So now we can calculate the approximate value is 0.7 minus 65 millivolt minus 1.2 divided by 300 equal to minus 1.88 volt, minus 1.88 millivolt. So the slope, it is showing it as minus 1.88 millivolt. But in the beginning we said the slope is minus 1.6 millivolt per degree Kelvin. So why is this difference? This difference because of many reasons. First of all, we took the Eg as 1.2. So people will take Eg as 1.1 also, 1.1 electron volt also, and the voltage across the diode we took as 0.7 volt, and sometimes people will take it as 0.75 or 0.8 also. So according to that, this voltage, this value will change. So even in some textbook it is given as minus 1.5 millivolt per degree Kelvin. So I just substituted some approximate values to get a figure of how much it is how much it will come. So it will come near to minus 1.6 millivolt per degree Kelvin. So if you put exact value of Vd and exact value for energy value, that is Eg, then you will get the value of the dou Vd by dou T. But for the design of the band gap, we just need to understand the slope of the CTAT will be near to minus 1.6 millivolt per degree Kelvin. This expression is extremely important, and we will come back to this later in the discussion.